Welcome to GATE class. In this class, we will discuss the various properties of Z transform. The first property is linearity property. So, according to this property, if x1 has Z transform x1z with ROC R1 and x2n has Z transform x2z and the ROC is R2, then if we give the combined signal, A1 A1 x1n plus A2 x2n has the Z transform, that is equals to A1 x1z plus A2 x2z, and the ROC is basically R dash that belongs to R1 intersection with R2. So the ROC is R dash and this belongs to R1 intersection with R2. So this is our linearity property. This is our linearity property. That second property is The second property is called time shifting property. The second property is called the time shifting property. So according to this property, if x1 n, if xn, let it is xn, better to take xn. If xn has Z transform xz, so if xn has Z transform xz and the ROC is R, let the ROC is R, then if we find out xn minus n naught, then the Z transform will be equal to Z raised to the power minus n naught into xz, and the ROC is equal to R dash, and that is equal to R intersection with 0 is less than modulus Z less than infinity. So this is the new ROC. This is the new ROC. So there are some special case. So what is the special case? So there is some special case. So if we consider xn minus 1, then the Z transform is equal to Z raised to the power minus 1, because n naught is 1 here, Z raised to the power minus 1 into xz, and the ROC is R dash, that is it belongs to R intersection with 0 is less than 0 is less than modulus of Z. That is the ROC. Now if we consider xn plus 1, then it is Z raised to the power 1 into xz according to this property, and the ROC R dash belongs to R intersection with modulus of Z less than infinity. That is modulus of Z less than infinity. Now because of this relation, because of this relation, relationship, the Z inverse is often called the unit delay operator. Z inverse is often called the unit delay operator. So Z inverse is often called the unit delay operator. And please note that one of the important point we need to note that. So note that in the Laplace transform of our operators, in the Laplace transform of In the Laplace transform of operators, S inverse is equals to 1 by S. That S inverse is equals to 1 by S, and S corresponds to the time domain integration, and S corresponds to the, and so S inverse it equals to 1 by S, and S corresponds to time domain integration and differentiation respectively. So basically S inverse 1, that is equals 1 by S, and S corresponds to the time domain integration and differentiation respectively. So all these are related to each other. So if you are going to discuss the Z transform, then the that continuous time counterpart is the Laplace transform. Let us discuss the third property. That property is called the multiplication by. That property is called the multiplication by Z0 raised to the power n. So Z0 is some constant quantity. So what is Z0? So Z0 is some constant quantity. So let us discuss this property. So if Xn has Z transform, if Xn has Z transform Xz, and the ROC is R, if Xn has some Z transform Xz and the ROC is R, then Z raised to the power n Xn, the Z transform is equals to Xz divided by Z naught. And what is the ROC? So ROC is R dash, and it is equals to modulus of Z naught into R. So this is the new ROC. So the ROC is just it is getting multiplied by some constant value of Z naught and with old ROC. So in particular, so we can say that in particular a pole, and of course or zero also. So in particular a pole or zero at Z is equals to Zk in Xz, Z is equals to Zk in Xz changes to, so moves to, better to say that moves to, because we are going to change the location of the poles. So that pole or zero will at Z is equal to Zk moves to Z is equals to Z naught into Zk. Z is equals to Z naught into Zk after multiplication by Z0 raised to the power n, and the ROC expands, or contracts, and the ROC expands or contracts by the factor. So which factor it is going to contract or expand? So the factor is modulus of Z naught. So by this factor it is contracted or expanded. So this is called the multiplication by Z0 raised to the power n property. Now let us discuss the another property, and this property is called the time reversal property. So this property is called the time reversal. This property is called the time reversal property. So according to this property, if Xn has Z transform Xz, and the ROC is R, the ROC is R, then if we find out, then if we time reverse, if we find out x minus n from xn, that is getting after the time reversal of xn, then z try, we find out the z transform of x minus n, then it is equals to x1 divided by z. And what is the new ROC? So the new ROC is, let it is R dash, and R dash is nothing but it is equals to 1 divided by R. That is the new ROC. So therefore, a pole or zero in xz at z is equals to zk, moves to 1 divided by zk after the time reversal. After the time reversal, the relationship R dash is equals to 1 divided by R indicates that the relationship R dash is equals to 1 divided by R indicates that the inversion of R indicates the inversion of R, that is original R was ROC of xn, then R dash is equals to 1 by R is the ROC of the Z transform of x minus n. So it is reflecting that it is reflecting that a right-sided sequence, so if we have a right-sided sequence, so it is reflected that a right-sided sequence becomes left-sided. So now previously you have right-sided sequence, now it will become the left-sided sequence. So this is called the time reversal property. So let us discuss another property. That property name is multiplication by n. Multiplication by n. So this property is called the multiplication by n. So if xn has z transform xz and the ROC is equals to R, then if we multiply with nxn, then what will happen? The z transform is minus z dxz divided by dz, and the ROC is surprisingly the R dash, that is equals to R. Surprisingly the ROC is not changing, the ROC is again the same. So the differential multiplication by n will not change the ROC will remain the same. Next property is called the accumulation property. Accumulation property. This property indicates that if we have xn and the z transform of this is xz, the ROC is R, then summation k is equals to minus infinity to k is equals to plus infinity xk has the z transform, that is 1 divided by 1 minus z inverse into xz, and the new ROC, that is R dash, it belongs to R intersection with modulus of z greater than 1. So this is our new ROC, that is our new ROC. Next property is convolution property. Next property is convolution property. So according to this property, if x1n has z transform that is equals to x1z and the ROC is R1 and x2n, there is another discrete time sequence and the z transform is let it is x2z and the ROC is R2. Then if we find out the convolution of x1n with x2n, then z transform is equals to x1z multiplied by x2z and the ROC is nothing but R dash, that is belongs to R1 intersection with R2. So this ROC is R dash, that is intersection of R1 with R2. So this is called the convolution property. There is another property that is called the inverse Z transform. That is called the inverse Z transform. So xn is if we find out xn from xz, that is z transform is given, so xz is given, and if we find out the xn, that is inverse z transform of this, so that is equals to z inverse of xz, and that is equals to 1 divided by 2 pi j, that is closed contour. It is basically the closed contour, and the formula is like this. And basically that C is, so what is C? So C is the counterclockwise. C is the counterclockwise contour of integration enclosing the origin, enclosing the origin. So C is the counterclockwise on contour of integration enclosing the origin, Now let us discuss the partial fraction expansion. So let us discuss the partial fraction expansion. So as in case of inverse Laplace transform, the partial fraction expansion method, so we have used in case of Laplace transform to find out the inverse Laplace transform, and we have used that partial fraction expansion analysis. So as in the case of Laplace transform, the partial expansion, the partial fraction expansion method, the partial fraction expansion method provides the most generally useful inverse of, so provides the most general useful inverse of Z transform, and especially when xz is a rational fraction of z. Xz is a rational fraction of z. So let us denote xz as nz divided by dz. Let xz is equals to nz divided by dz, and it is written as k multiplied by some z minus z1, z minus z2 up to z minus zn. Then we have z minus p1, z minus p2 up to z minus pn. So what is z1, z2, zn? So better to take m here because we have to differentiate between m and n, because the number of poles and number of zero may be equal or non-equal. So this z1, z2 up to zm, so these are basically zeros. These are basically zeros, and p1, p2, pn, these are poles of the transfer function of the system. So these are poles and these are zeros. So we can assume that, assuming n is greater than or equal to m, so that number of poles in denominator is greater than the number of poles in denominator. So number of zeros in numerator. So number of poles in denominator, that is dz, that is a number of poles in denominator is greater than the number of zeros. So if we assume that n is greater than or equal to m, and all the poles are simple. So we have just assumed that the simple poles are there. Then this xz divided by z is written as c naught divided by z plus c1 divided by z minus p1 plus c2 divided by z minus p2 plus dot 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 plus cn divided by z minus pn. So let this equation, that previous one, so let this is equation number 1, and this is equation number 2. Xz divided by z, we can find out xz divided by z by this relation, and we can summarize these terms. We can write in the form of summation. So it is nothing but it is equals to c naught divided by z plus k is equals to 0 to n ck divided by z minus pk. Now what is c naught? So where c naught is xz when we have z is equals to 0, and what is ck? So ck is z minus pk multiplied by xz divided by z when we have z is equals to pk. So this is equation number 5, and this is equation number 5, and this one is equation number 4. So now what we can do, so we can obtain this xz as, hence we obtain xz, and that is xz is equals to c naught plus c1 z divided by z minus p1 plus dot 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 plus cn z divided by z minus pn. So this xz is equals to c naught plus summation k is equals to 1 to n ck z divided by z minus pk, and this is equation number 6. So this is equation number 6. This is equation number 6. So we can consider various conditions. So if m is greater than n in equation number 1, then a polynomial of z, must be added to the right hand side of 6, must be added to the right hand side of 6. The order of which is m minus n. The order of which is m minus n. So what is happening here? Thus for m greater than n, the complete partial fraction expansion would have the form, that is xz is equals to summation q is equals to 0 to m minus n bq z raised to the power q plus k is equals to 1 to n ck z divided by z minus pk. So if xz has multiple order poles, so suppose if xz has multiple order poles, so if xz has multiple order poles, so say pi is the multiple of pole with multiplicity r, then the expansion of xz divided by z will consist of the form that is given as lambda 1 divided by z minus pi plus lambda 2 divided by z minus pi square plus plus lambda r divided by z minus pi raised to the power r. So what is lambda r minus k? So lambda r minus k is 1 divided by k factorial d raised to the power k divided by dz raised to the power k z minus pi raised to the power r xz divided by z, and we are putting all these we are putting the value of z is equal to pi in this resulting equation. So we will see some examples when we will do the inverse z transform. Then we will do this partial fraction analysis, and we will do some examples related to this. So we will understand much better when we will solve some numerical problems. So let us describe the system function. So let us describe the system function. So the next topic is the system function of discrete time LTI system. The system function of discrete time LTI, the system functions of discrete time LTI systems. So the system function is, yn. How to find out the system function, that is sz. So the system function can be find out by using this relation, that is yn is equals to xn convolution with hn. And if we find out the z transform, then what we will get, the z transform of yn is yz, the z transform of xn is xz, and the z transform of hn is sz. That is nothing but the system function. So hz is equals to yz divided by xz, and that is the system function. That is the system function. This is called the system function. So the z transform, the z transform of hz, that the z transform of hn, that is hz, is referred to as the system function, and sz is equals to summation n is equals to minus infinity to plus infinity hn z raised to the power minus n. So there are various characterization of the system function. So characterization of LTI system in terms of Z transform. That characterization of LTI system in terms of Z transform. We have studied the characterization of LTI system in case of continuous time, in continuous domain, that we are performing this characterization by using the Laplace transform. Here we are going to basically we will consider the Z transform for characterize the LTI discrete time LTI system. So first characterization is causality. The first characterization is causality. So for a causal discrete time LTI system, we have Hn is equals to 0. The impulse response is equals to 0 for n less than 0. So this is the definition of a discrete time LTI system. So since Hn is right-sided, signal, because Hn is equals to 0 for n less than 0, so it is a right-sided signal. So the corresponding requirement, of Hz, the corresponding requirement of Hz is the ROC of Hz is the ROC of Hz must be of the form modulus of z should be greater than R max. Modulus of z should be greater than R max. So we can say that is the ROC is the exterior of a circle. The ROC is the ROC is the exterior of the circle that we have seen in case of a raised to the power n un, when we have xn is equals to a raised to the power n un. Then the ROC is mod z greater than mod a, so it is just exterior to that circle. It is just exterior to that circle. Since the ROC is exterior of the circle containing all the poles of xz, containing all the poles of sz, containing all the poles of sz in the z plane, So similarly, if the system is anti-causal, so the system is anti-causal. So what is that anti-causal? That is Hn is equals to 0 for n greater than or equal to 0. Then Hn is left sided, and the ROC of sz must be of the form modulus of z is less than R minimum. Modulus of z is less than R minimum. So that is the ROC is the interior of a circle. That is the ROC is the interior of the circle. So basically, if we have xn is equals to minus a raised to the power n u minus n minus 1, then the ROC is interior. The ROC is interior to the circle because it is modulus of z less than modulus of a. So this is interior of the circle when it is anti-causal. So this is basically the anti-causal signal. This is anti-causal signal. This is anti-causal signal. So we have second characterization, that is called the stability, and that is very important criteria. So we know that for a discrete time LTI system is bounded input, bounded output is stable if we have the condition that is from n is equals to minus infinity to plus infinity, modulus of Hn should be less than infinite. So this is the condition for bounded input, bounded output stability. So this is the condition for bounded input, bounded output stability. So similarly, if we just talk in terms of Z transform, so the corresponding requirement of Sz, the corresponding requirement of Hz is that the region of convergence of Sz, the region of convergence of Sz contains the unit circle, contains the unit circle. So if we have Z transform, suppose this is unit circle, and if this is the Z transform, suppose some point A is there. Now if the Z transform, the ROC is containing the unit circle, then it is stable. And if we have if we have this unit circle, and if the ROC is like this, if the ROC is like this, then this is unstable system. This is unstable because in this case the ROC contains the unit circle. The ROC contains the unit circle, and in this case the ROC does not contain the unit circle. So in this case the ROC does not contain the unit circle, and here in this case the ROC contains the unit circle. That's why it is stable, and this system is unstable because it does not contain the unit circle. So what is that causal and stable system? If we say that causal and stable both, causal and stable both, if we say that the system is both causal and stable, so if the system is both causal and stable, then all the poles of SZ, that is the SZ is the transfer function, must lie inside the unit circle of Z plane, inside the unit circle of Z plane, inside the unit circle of Z plane, because the ROC is of the form modulus of Z is greater than R max, and since the unit circle is included in the region of convergence, so we must have R max less than 1. It means if we have suppose we have mod Z greater than 1 by 2, then this is unit circle. So basically we have the ROC, that is all the poles. So basically that poles is inside the unit circle. So if we have poles at Z is equals to minus 1 by 2, Z is equals to minus 1 by 3, Z is equals to minus 1 by 5. So all these poles are on left hand side, all the poles on left hand side, and their magnitude is obviously less than 1. So all these poles are inside the unit circle. So all these poles are on left hand side and magnitude is less than 1. So all the poles are basically inside the unit circle. So since it is a causal signal, so the maximum is 1 by 2, so that R max, so here R max is 1 by 2, here R max is 1 by 2, and mod Z is greater than 1 by 2. So this is an example. So this type of signal is that both causal and stable when all the poles of SZ must lie inside the unit plane, inside the unit circle, and also that stability they must lie in left hand side. So next is we have system function of LTI system. Now we have system. So next is system function for LTI system or LTI systems described by linear constant coefficient differential equation, described by linear constant coefficient differential equation. So we have some linear constant coefficient differential equation model, and we will see the Z transform aspect. We will try to solve this by using the Z transform aspect. So the equation is like in this form: k is equals to 0 to capital N a k y n minus k, and that is in it equal to is small k is equals to 0 to capital M b k x n minus k, and we can apply the Z transform. So applying the Z transform and using the time shift property applying the Z transform and using the time shift property and also linearity property So what we will get summation k is equals to 0 to capital N a k z raised to the power minus k into yz is equals to summation k is equals to 0 to capital M b k z raised to the power minus k into xz. So this is our relation, or we can also write in the another form, or it is written as yz summation k is equals to 0 to capital N a k z raised to the power minus k is equals to xz summation k is equals to 0 to capital M b k z raised to the power minus k. So thus we have sz, we have the system transfer function sz is equals to yz divided by xz, and from this relation we can find out that summation k is equals to 0 to capital M b k z raised to the power minus k is divided by summation k is equals to 0 to capital N a k z raised to the power minus k. So this is our relation, this is our transfer function, hence hz is always rational. So let us discuss then another property that is called the system interconnection. System interconnection. So for the LTI systems with impulse response h1n and h2n respectively. So we have two impulse responses h1n and h2n. If these two impulse responses in cascade For the LTI system, H1 and H2 are in cascade. The overall impulse response, Hn is given by Hn is equals to H1n convolution with H2n. And if we find out the Z transform, what we will get here, Hz is equals to H1z multiplied by H2z, and the ROC is basically R1 intersection with R2. That ROC is basically the R1 intersection with R2. So this is the ROC. There is one important term, that is the unilateral Z transform. The unilateral Z transform, there is another important property. So the unilateral or one-sided Z transform X1Z of sequence X1n is given as X1Z is equals to summation n is equals to 0 to n is equals to infinity. So instead of taking from minus infinity to infinity, we are going to take that value of n small n from n is equals to 0 to infinity, and it is xn z raised to the power minus n. So it is equals to xn z raised to the power minus n. So this is basically the unilateral or one-sided Z transform. So let us solve one problem. Consider the sequence xn, and that is equals to a raised to the power n when we have small n, that is between 0 to n minus 1, and a is greater than 0, and it is equals to 0, otherwise. So the question is find xz and plot the poles and zeros of xz. Find the poles and zeros of xz. So the answer is the xz is equals to, let us find out the xz. So xz is equals to summation n is equals to minus infinity to plus infinity xn z raised to the power minus n, and since we have xn between 0 to n minus 1 only, so it is equals to 0 to capital N minus 1, and the value is an z raised to the power minus n. Now this is a finite ZP, so the solution is, please check, the solution is z raised to the power n, a raised to the power n divided by z raised to the power n minus 1 and z minus a. So this is the solution for this. So this is xz, that is the Z transform. So if we see that, we can find out that there is a pole of n minus 1 order here. So we have a pole of n minus 1th order. So there is n minus 1th order pole at z is equals to 0. Please see that at z is equals to 0, we have n minus nth order, capital N minus 1th order pole is there, and one pole at and one pole at z is equals to a. So we can see here we have another pole. We have another pole that is at z is equals to a. So the nth root of the polynomial, the nth root, please find out that what is the nth root. So the nth root of numerator, the nth root of numerator polynomial is zk, and that is equals to a e raised to the power j 2 pi small k divided by capital N and the k is from 0, 1, 2 to capital N minus 1. So we have the root at k is equals to 0 cancel pole at z is equals to a. So the root at k is equals to 0 cancel pole at z is equals to a. So we can clearly see from this expression also. So the remaining poles are zk is equals to a e raised to the power j 2 pi small k divided by capital N, and that is k is equals to 1, 2, 3 to up to capital N minus 1, because 1 is already cancelled out. So we can just plot this. So we have, this is z plane, so this is z plane, and we have these are zeros, and there is a pole, so at origin, so this is basically n minus 1th order pole, and that pole 0 cancellation is there. So there pole 0 cancellation is there. So this is a real part of Z, and this is the imaginary part of Z. So this is the typical pole 0 plot, and this is the Z plane. Because Z is a real part of Z plus J into imaginary part of Z, because Z is a complex number. Let us solve one problem. So show that if xn is a right-sided sequence and xz converges for some value of z, then the ROC of xz is of the form, mod z is greater than R maximum, or infinite is greater than mod z, and that is greater than R maximum. So what is R maximum? So where R maximum is the maximum magnitude of any of the poles of xz, xz. So let us solve this problem. So let us solve this problem. So consider a right-sided signal. Consider a right-sided signal, right-sided sequence xn, so that what we are getting xn is equals to 0 when we have n less than capital N1, and xz converges for modulus of z is equals to r naught. So xz is equals to summation n is equals to minus infinity to plus infinity xn z raised to the power minus n. Since modulus of z is equals to r naught, so we obtain, since modulus of z is equals to r naught, we obtain modulus of xz is equals to it is less than or equal to n is equals to minus infinity to plus infinity modulus of xn r 0 raised to the power minus n, because we have considered that magnitude of z is equals to r naught. So what we are getting here, it is equals to summation n is equals to n1 to infinity modulus of xn r0 raised to the power minus n, and that is less than infinity. Obviously it is less than infinity. Now consider, now if there is another r1, that is this constant value, that is greater than r naught, then what will happen? This summation n is equals to capital N to infinity modulus of xn r1 raised to the power minus n is equals to n is equals to n1 to infinity modulus of xn r naught r1 divided by r naught raised to the power minus n, and that is equals to summation n is equals to n1 to infinity modulus of xn r0 raised to the power minus n r1 divided by r naught raised to the power minus n, and that is equals to r1 divided by r naught raised to the power minus n1 summation n is equals to n1 to infinity modulus of xn r0 raised to the power minus n less than infinity. So since r1 divided by r naught raised to the power minus n is decaying sequence, it is decaying sequence, thus xz converges for r is equals to r1, and the ROC xz is of the form modulus of z is greater than r naught. So since the ROC of xz cannot contain any poles of xz, cannot contain any poles of xz, since the ROC of xz cannot contain any poles of xz, so we conclude that the ROC of xz, so we conclude that the ROC of xz is of the form modulus of z is greater than r max. And what is r max? So where r max is the maximum magnitude, So R max is the maximum magnitude of any poles of xz, of any poles of xz. So if n1 is less than infinity, then we can write it as xz is equals to summation n is equals to n1 to infinity xn z raised to the power minus n, and that is nothing but it is equals to xn1 z raised to the power minus n1 plus dot 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 plus x minus 1 z raised to the power 1 plus summation n is equals to 0 to infinity xn z raised to the power minus n. So what will happen that that is xz contains the possible powers of z and becomes unbounded at z is equals to infinity. So in this case ROC is of the form infinite is greater than mod z is greater than R max. So ROC is of this form, infinite is greater than mod z and mod z is greater than R max. So from this result we can tell that, we can tell that a sequence xn is causal, and is not basically the system is causal not just right sided from the ROC of xz if z is equals to 0 is included. So let us do another problem. The problem is we need to find out the z transform of xn, that is given as 1 divided by 2 raised to the power n un plus 1 divided by 3 raised to the power n un. So this is a very typical z transform questions that are coming in GATE regularly. So what is a z transform, that is xz? So it is 1 divided by 1 minus 2 z inverse. Please check, and this is equals to 1 minus 1 divided by 3 z inverse. So this is our z transform. The ROC is mod z greater than 1 by 2, and here the ROC is mod z greater than 1 by 3, because both signals are right sided. Both x1, since x1 and x2 are both right sided, x1n and x2n are basically right sided causal signals. So both have causal signals. So we can find out this ROC, that is exterior, always exterior. So we have 1 by 2, a circle of 1 by 3 and another circle of 1 by 2. So the ROC is exterior to the outermost pole, whatever we have. So that our pole is basically at z is equals to 1 by 2 and z is equals to 1 by 3. So these are two poles we have. First pole is 1 by 2 and second pole is 1 by 3. The ROC is modulus of z greater than 1 by 2. So the ROC is modulus of z greater than 1 by 2. Modulus of z greater than 1 by 2. So this is the ROC.